Hello everybody. So this is one extra video that I was not planning to make, but this was a question that I was asked about the tearing process. Um, and this question was about the reactor, especially because the reactor is the one that is most it's not complicated, but most detailed unit regarding the equations compared to the rest of the units. So for the reactor, the case that we solved last time was a very straightforward case. We were able to calculate the extent of reaction very easily. And as we know, the extent of reaction makes us able to calculate everything else. So this is something that we did last time. Now the question is, what if the reactor will not be solved in a straightforward way and we have to solve equations simultaneously? And this is a very common case. So that's why I made this modification to the problem. So we have the same problem, but instead of having only one reaction, there is one side reaction that we have here. Which is so the main reaction was the reaction of ethylene and benzene to produce ethyl benzene, and the second is that ethyl benzene reacts with ethylene to produce diethyl benzene. And based on this, you can see that we have diethyl benzene in the product, and we have diethyl benzene in stream 5, of course, and there is some diethyl benzene that comes here, which is mixed with the fresh feed, so there is diethyl benzene here. So all the streams except the fresh feed contain diethyl benzene. And we have two information about the reactor. We have the conversion, the fractional conversion of ethylene, which is the same, but it's now for two reactions, not only one reaction. And we have the selectivity of ethyl benzene to diethyl benzene. And we discussed the selectivity before, and we said it's the number of moles of the desired product divided by the number of moles of the undesired product. So this is the number that we have here. We still have the same relations for the separator, and there is one extra relation regarding the diethyl benzene. So we say that 2% of the diethyl benzene is recycled and the rest is coming as the bottom product. And we now want to perform degrees of freedom analysis and see what we can do regarding the solution of this problem. So for the mixer, we have 5, so it's 15, and 3, so it 5 is 10 plus 3 is 13. I'm sorry. And we have 3 given variables. We have 5 equations because we have 5 species, and we have no additional relations, so degrees of freedom is 5. For the reactor, we have 5, which is 10, and we have 2 extents of reaction, so it's 12. We have no given variables. We have 5 equations, and we have 2 additional relations, so it makes the degrees of freedom is 5. For the separator, we have 5, so it's 15 variables. We have no given variables. We have 5 equations and 5 additional relations, which is 1, 2, 3, 4, 5 additional relations. And this makes the degrees of freedom 5. For the overall, we have 1, 2, 3 plus 5, it's 8, and 2, so it's 10 variables. We have 3 given variables. We have 5 equations. And we have no additional relations, so the degrees of freedom is 2. For the process, we have 3, and this is 1, 2, 3, 4 streams. Each contains 5 components, so this is 20, and this is 3, so it's 23 plus 2. This is 25 variables. The given variables are 3. So the number of unknown variables here is going to be 22. The number of equations is the summation of the equations of the 3 units, so it's 5 plus 5 plus 5, this is 15, and the number of additional relations is 7. These are all the additional relations we have. So if you calculate this process degrees of freedom, it's 0, which means, again, this is something that I stress on every time, that the process is 0 means that we cannot assume any information. So we have to deal with the given information that we have here. So we have 2 options, either to do the solution by solving the equations simultaneously, and in this case we have 22 equations, so we'll solve 22 equations in 22 unknowns using the matrices because they're all linear equations. And by the way, I have already done this. I just want to show you the matrix. It's a huge one. So this is 22 by 22. It's similar to the one that we did last time, but it's larger because we have more equations and more unknowns. And it worked. We have here all the components in all the streams, but as I told you, it's a very time-consuming process. If there is a wrong number, you have to keep tracking all the numbers to make sure that you figure out which number is the wrong number. But at the end of the day, it works. This is the take-home message out of this. And this is not what I want to discuss here, because we already discussed this before, and this is not adding anything new regarding the solution. So I'll go back to the slides, and the way we are going to do this here is by tearing. And tearing, as we said, we are going to tear stream number 4 into 2 streams, one assumed and one calculated, and we will assume this 5 components, and then we are going to feed them to the mixer, and then the mixer needs 5 information, so it's solvable. Now we have 5 information given to the reactor, which needs 5 information, so the reactor is solvable. We can solve or give 5 information to the separator, which needs 5 information, so separator is solvable. Now we can calculate stream 4 again, and we can compare the assumed and calculated, and do more iterations until it converges. So this is the plan that we are going to do. But now the trick was going to be regarding the reactor. For all of them, the equations are going to be very straightforward. They are very similar, or exactly similar to what we did before, with the exception of having one extra variable, which is the diethylbenzene. Otherwise, everything is the same. But for the reactor, if you list the equations, for the reactor we have 5 balance equations and 2 additional relations. So if we write the equations for the reactor, this is the ethylene, the benzene, the ethylbenzene, diethylbenzene, and inerts. And of course, the extensive reaction are depending on the stoichiometric coefficients that we have in the equation. So we have ethylene -1 in the 2 equations, so it's negative xi1, negative xi2. For benzene, it's only negative xi1. For ethylbenzene, positive xi1, negative xi2. For diethylbenzene, it is positive xi2. And inerts is not part of the reaction, so it's in equals out. Now we have here 5 equations in 7 unknowns. We will have all the 5 variables that in stream number 2. Stream number 2. These 5 variables are going to be known because we will assume them. So we have the 5 components in stream number 3 and the 2 extensive reactions. So this is 5 equations in 7 unknowns. So we need 2 extra informations, which are the additional relations. If you put the additional relations, both would be a function of 2 variables, which are the 2 extensive reactions. So when we say that the conversion of ethylene is 0.7, so 0.7 is the number of ethylene, the product, minus number in the feed minus the product over the feed. So ethylene in 2 minus ethylene in 3 is xi1 plus xi2 over number of ethylene, moles of ethylene in stream number 2. For the selectivity, it is number of moles of ethylbenzene over diethylbenzene, and we have the formulas for them already here. So it's going to be again function of xi1 and xi2. So now when we want to do this solution using Microsoft Excel, for example, then we have to find a way to calculate the 2 extensive reaction. It's not as straightforward as before, and we have to find a way. So there are 2 options that we have, and these are the 2 options I'm going to do in this video. The first option is to let the software solve these equations for me. So if you look at the equations, both of them are linear algebraic equations. So this is xi1 plus xi2 equals 0.7 multiplied by a constant or a number that we have, which is going to be part of the iterations. And this equation can be rearranged to be xi1 minus 16 xi2 equals this numbers, which is also part of the iteration. So these are numbers that we can give to the software. So we can solve them as a matrix. So we have this is the coefficients 1, 1, 1, negative 16, and the 2 extensive reactions xi1 and xi2 equals 0.7 in E2, and this is the same as this. So this is one thing we can do, that we can feed this information to the software and do the same operations for matrix calculations that we did last time, and the product would be fed to the loop of the iterations, and this will make the problem solved. So this is one option, and this I think this is not the easiest option here, because the equations are easy to solve together, as we will see in few minutes. But what I want to show here is that even if the equations are not easy to solve, let's say you have 3 equations and 3 unknowns, you have 3 reactions, you have 4 reactions, and you have 4 equations and 4 unknowns, or 3 equations and 3 unknowns, you still can apply this method, which would be easier than simplifying the equations that are not easy to simplify. So this is one option. The second option is to simplify the equation. So I can add equation or subtract equation 2 from equation 1. So if you subtract them, xi1 would be cancelled out, and then it's going to be 17. Xi2 equals this. So xi2 equals this over 17. So this is one way we can calculate xi2, and from xi2, this is flipped, but it's xi1 equal 0.7 Ne2 minus xi2. So this is going to be a very straightforward way. We can just type the formula, and using this formula we can directly calculate xi1 and xi2 instead of having the software calculating this for us. Again, this is not the easiest way to do this here. This is much easier, but this is a method that you can apply to any number of variables, which is not going to be as easy as this in this case. And in this case, this is not going to be an easy way if you have equations with many number of unknowns, 3 or 4 equations and 4 unknowns. So let's move now to the software and see what we can do. So this is the first method, which is going to be using the simultaneous solution of the equations. The software will solve the equations for us. So again, we are starting here with the given information. I added one extra row here for diethyl benzene, and we have here the feed flow rates that we have, and we will start first by assuming stream number 4. So again, the assumption needs to be a realistic assumption. So I would say that ethylene would be, let's say, 500, benzene is a little less, so it's going to be 400. The inerts, we know they accumulate, so I'll put 1000. Ethyl benzene, small amount, so I'll put 50, and diethyl benzene is a smaller amount because it's a side product, so it should be small amount, and only small amount of this small amount goes up here, so I'll put 5 or 10, whatever. So let's make it 10. Okay, so this is the assumed value, and from this assumed value we can calculate stream number 2, which is going to be the summation of stream 1 and the assumed value of stream number 4. And now stream 3 can be calculated from the extensive reaction. Now comes the interesting part. This is similar to what we did before, but this is the tricky part. So I'm going to write the matrix here for the coefficients. So it's 1, 1, which is the coefficients of these two variables, and it's 1 and negative 16, which are the coefficients of these two variables. And now I'll calculate the inverse here. So this is the inverse of the matrix, and now we will put the coefficients, which is 0.7 times Ne2. This is Ne2. And this is 15 times number of moles of diethyl benzene in stream 2 minus the number of moles of ethyl benzene in stream 2. And now we get the xis. Again, it's just solution of equation. It's the inverse multiplied by the product. So it is the M multiplication of this matrix by this matrix, and these are the extensive reaction. So the nice thing about this is that they will automatically be calculated based on the values that we have here. And for example, if I assume this to be 600, this will be calculated accordingly. So there's nothing that you can or you need to worry about. The numbers will be updated automatically, and you can use these now to calculate stream number 3. So I know that the ethylene is the ethylene in stream number 2 minus xi1 minus xi2. For benzene, it is benzene in stream number 2 minus xi1. For inerts, it's the same. For ethyl benzene, it is this plus xi1 minus xi2. And for diethyl benzene, it's in the feed plus xi2. So now the reactor is done. And now we can calculate stream number 4 and stream number 5. And again, stream number 4 is calculated from the additional relations. And by the way, what we're doing here is something we can do with anything else here. For example, if you have the same thing for the separator, you have equations that need to be solved simultaneously. You can solve them outside and then get the output to be fed to the loop. So it's something you can definitely do. It will need some manipulation of the equations, making sure that you put them in a proper way. And this is part of the solution, by the way. It's not just something that you just put. You need to prepare for this beforehand. So the calculated stream 4 for ethylene, it is the ethylene, the feed times 90%. For benzene, it's benzene times 80%. The innards, it's the innards times 70%. For ethyl benzene times 5%. For innards, it is innards times 2%. So we calculated all of them, and stream number 5 is 4, it's not 4, it is 3 minus 4. So this, I think there's something wrong here. It's stream number 3 minus stream number 4. So yeah, there are going to be some differences because I think I did something wrong here. So 4 calculated is calculated from stream 3. Oh, I always do this mistake. So it's calculated from stream 3, not from stream 4. I'm calculating 4 from 4, which is a big mistake. So it's calculated from stream 3. You have to be careful. And again, this is something that's very common. So you have to make sure that you write the proper equations. It's very, very, very probable that you'll do mistakes. So it's totally fine. Just make sure you have a feeling of the numbers, and you make sure that you have a good way to track the calculations, and make sure you can find where is the mistake. So troubleshooting is a very, very important skill, so you have to acquire this skill well. So now we have everything done. So what we need to do is to change these numbers in order to make this is the square of the differences, so it's the same, to make the differences minimum or 0. So what we will do is exactly what we did last time. I'm using the solver to set this cell to 0 by changing these 5 cells. And let's see what we have. So it's now solving. It said it found the solution. If you look at the numbers, these numbers are not very small numbers, and keep in mind that they are squared, so the actual difference is bigger. And this is what you can see here. These two numbers are not, they're close, but they're not the same. The same here. There is a little difference. It's some differences. So it's not very, very accurate. It's very close. You can see it's very close, but it's not very accurate. So we can. One trick you need to know about solver is that the solver has what we can call the maximum number of iterations. So it will do, let's say, 100 changes in the values, and it will stop after 100. And it will assume that it's done with the solution. So maybe it took many iterations because we were not very close to the answer, or because the conversions takes time. So it takes many steps to reach the solution. So one thing we can do is we can ask it to do the solution again, starting from here. So now we are very close. So we will start from a very close point, which is something that will make the solution very very easy for the software. So if you look at the differences now, they're much better than before. Last time it was 10 to minus 2 to power minus 3. Now it's power minus 14 and 12 and 21 even. So this makes the solution much more accurate than before. And if you compare the numbers that we have here with the numbers that we got from the matrix solution, you would see here for stream number 2 these 4 numbers, and look at these 4 numbers. They're exactly the same. For the extents of reaction, these are the 2 extents of reaction. So we're getting the same results, which is very, very good news. So this is one way you can do this. The second way is going to be the same. So just to save time, I'm going to copy everything, and I'll do little changes just to start without wasting a lot of time. So I'm removing the assumed values, and here we have no formulas for the extent of reaction. I'm not doing the matrices now. I'm going to use these formulas for calculating Xi1 and Xi2. So Xi1 is 0.7 times Ne2 minus Xi2, and Xi2 equals 1/17 times 0.7 times number of moles of ethylene in 2 plus number of moles of ethylbenzene in 2 minus 15 times diethylbenzene in 2. Of course, these numbers are not the actual numbers because we haven't assumed stream 4 yet, but I'm just writing the formulas. So it's, again, I'm just checking. It is ethylene and ethylbenzene, it's not benzene. So ethylene, 0.7 times ethylene plus number of moles of ethylbenzene minus 15 times diethylbenzene. So again, make sure you check the numbers and check the formulas. One wrong symbol or one wrong cell in this formula can ruin everything. So again, I'll assume the same numbers I started with. So this is 600 now, and we assume that, if I'm not mistaken, this is 400 and this is 1000. The ethylbenzene was 50 and this was 10. I think these are the numbers that we started with in the beginning, and we will do the same thing. We will use the solver to change, set this cell to 0 by changing these 5 cells, and we will solve. Again, we have the same issue that we had last time. We're not the exact same values here, so we can run the solver one more time to have more iterations, and again we are getting, I think it's exactly the same numbers that we got last time. But anyway, so this is, if you compare the numbers that you have here and the numbers that you have here, I think that the easiest way is to look at these two numbers, the Xi1 and Xi2. So it's exactly the same numbers that we got. So the result that you get is the same. I think, of course, this is easier. It requires some mathematical work that you will do with the equations. So if it's easy, I would go for this. If you have more equations with more unknowns, I would pick this solution, because yeah, you don't need to do all this mathematical work yourself, especially if it's 3 or 4 equations. So I hope this helps and clarifies how to deal with these kind of problems. Goodbye.